All right, I'm back. I'm on page 263. It's a pretty crappy day outside. It's raining. We're all self-isolating, so I got time, so why not? Page 263, it says it right at the top. This is a dense but important page. There's actually only two problems to do on this entire page, but everything that you see here is going to stay with you like forever. Like you're going to have to know this stuff, reference it, use it, think about it. So the first thing, laws of continuity. So if f of x and g of x are continuous at the point x equals a. So this is a big deal. If they're both continuous there, what does it mean to be continuous? Limit exists, function exists, limit equals the value of the function, right? So if f and g, are both continuous at x equals a, then the following functions are also continuous at x equals a. So this is good because we want to be able to use this. So you got the sum and difference, right? So f plus or minus g, that's good. The product, f times g, definitely good. A constant multiple. So this one's weird. You don't use this property all that much because you just don't think about it. But if c is an element of the real numbers, then a constant multiple of f of x will also be continuous at x equals a. Like there's no reason that it wouldn't be. And then you're never allowed to divide by 0. That's basically one of the rules. F of x over g of x. So the quotient will also be continuous as long as g of a is not 0. So it's just 4 rules. You're going to use them all the time. You'll probably never really think about it, but you should definitely think about it because it's going to come up time and time again. All right, continuity of polynomial and rational functions. If p and q are polynomials, then p of x is continuous for all real numbers. Part of what makes polynomials the ultimate when you're dealing with functions. In fact, things that aren't polynomials, one of the things you'll do in Calc 2 is you will write polynomials that approximate them because polynomials are so easy to work with that we would always prefer to use a polynomial if we could. And then a rational function is no different from just general functions, right? So p of x over q of x is continuous at all values of x as long as the denominator is not 0. So you can never divide by 0. It's always going to be a problem. A couple of other things. Sine and cosine continuous everywhere. You know that because they're easy to graph. Everywhere on the reals. For like weird reasons, tangent is actually continuous on its domain, but it is not continuous on the reals, right? So tangent exists everywhere between, for example, negative pi over 2 and pi over 2, right? That's that one nice period of tangent. Everywhere between negative pi over 2 and pi over 2, the limit equals the value of the function, continuous. Negative pi over 2 and pi over 2 aren't in the domain, so they don't actually mess it up. Like you don't have to be continuous at a point that's not in your domain. So tangent is continuous on its domain, but there are values, real numbers, where tangent doesn't exist, so it's not continuous on the real numbers. So that's like a weird subtle distinction that you sometimes have to make, but you don't want to think about it too much, but think about it a little bit. Take a couple seconds, think about it. What other functions? 1 over x. 1 over x, everywhere it exists, the limit equals the value of the function. But at x equals 0, 1 over x doesn't exist. 1 over x is not continuous for all reals, but it's continuous on its domain. Every value in the domain, limit exists, function exists, limit equals the value of the function. All right, getting back to the notes. So these are continuous. Exponentials in general, as long as b is greater than 0, technically b shouldn't be 1. But actually it doesn't matter for these purposes. Exponentials are continuous. B is greater than 0 and b is not equal to 1. Then the log base b of x is continuous on its domain, so for x greater than 0. And then if n is a natural number, then f of x equals x to the 1 over n is continuous on its domain. So if n is odd, if n is odd, then that's all reals. Is it, God, what am I writing? All reals is domain, right? So like cube root, you can take cube root of anything, not a problem. If n is even though, then you're gonna have a lot of trouble taking the square root of a negative and getting a real number, right? So if n is even, then x has to be greater than or equal to 0. So like 4th roots, 6th roots, 54th roots, the domain will be greater than or equal to 0. 53rd roots, all reals, but they'll be continuous on their domains. Continuity of the inverse function, you know what, like, don't even worry about this one. But you can read it. If f is continuous on an interval I with range r, and if the inverse exists, then f inverse is continuous on the domain R. So like, think about it, right? So you got your function that's maybe like this, right? So this is your domain, and then this is R, it's continuous. And then the inverse, so if this is f, now I got to draw the inverse of this. I regret this. The inverse would be like, I think the inverse would be like that. They should be reflections over y equals x. I did my best. The inverse will have domain R and then range I. It doesn't really matter. It matters, but it's like not a super important thing, and it doesn't really come up anywhere else. And I don't know why I insist upon including it here, but I did. Continuity of composite functions. So this is one where it's like easiest to just like try it and see what happens. But if capital F, this is a thing in math. Capital F and lowercase f will appear in the same problem over and over again going forward. Capital F equals lowercase f of g of x is a composition of functions. If g of x is continuous at x equals a, which just means that the limit equals the value of the function, and f is continuous at g of a, because that's what we're going to sub in, right? If x is equal to 3, you're going to find g of 3 and take g of 3, try to sub it into lowercase f. So if lowercase f is continuous at whatever g of a is, then capital F is continuous at x equals a. You actually use this property a lot, and you'll see it in action a couple of places, but in general, you don't have to worry about it a ton, but it's a thing. And then this is the most important thing on this page, I would say. In fact, let me bust out a highlighter of some sort and maybe make it really big. Holy cow, that is huge. Here we go. This is it. This is it, right? This is the most important thing on the page. So this is, let me go back to a normal size highlighter just in case. The substitution method of evaluating limits using continuity. If a function is known to be continuous, then the limit is equal to the value of the function. So we can evaluate the limit by just evaluating the function. That's what you're going to do all the time. So this is, and we've done it like a lot, but that's what allows you to do this. So here, if I have to find the limit as x approaches pi over 6 of cosecant of x, really quick review, cosecant, right? So sine 2 pi, and then, so I'm going to graph sine, but I'm going to graph it dotted and maybe in a different color. So sine. There you go. All right, so cosecant, reciprocal of that, going to have vertical asymptote here. It's going to have a vertical asymptote here. And then its function, we'll hit it here and here. We go up. Should have done this in a different color too, but I didn't. So we would have problems at 0, at pi, basically multiples of pi. Pi over 6 is not an integer multiple of pi. So the limit as x approaches pi over 6 of cosecant, ew, what am I writing here? Cosecant of x should actually just be equal to the cosecant of pi over 6, because cosecant is continuous at pi over 6. And the sine of pi over 6 is 1/2, so the cosecant is 2. That's the you can evaluate just by the fact that it's continuous. All right, let's see. This thing has a domain of x has to be greater, not greater than or equal to, just greater than -8. Because if it's equal to -8, you're trying to divide by 0, always a problem. So radical x plus 8 is continuous everywhere on its domain. 2 to the x plus 2 is exponential, continuous everywhere. So this should just be equal to 2 to the -4 plus 2 over square root of square root of 4, let's say. So that's 2 to the -2 over 2, which is 1/8. So that's a limit. So we evaluate it just by evaluating the function, which is like the best thing that can happen to you. Like, honestly, most limits can be done that way, but you won't be asked about those. You're usually asked about more interesting problems where things go wrong or a little weird. You got to look from the left and the right and deal with all that stuff. But if you can evaluate them this way, you should evaluate them this way. So I'm going to cut this video here, and I will be back to talk to you more about more of this stuff. I hope you're finding this helpful.